Hi guys, here's the review video for equilibria and equilibrium constants, and I'll start this off by talking a little bit about what an equilibria is, and then we'll move through and talk about how to solve for equilibrium problems. So here we go. So here's a reaction, and we've actually looked at this before. This same reaction where we look at H2 and I2 going to HI. And so if you look at what happens here over the course of time, there are a couple of things to recognize, right? First off, let's look at this. All reactions are considered to be reversible. And so if all reactions are reversible, they establish some sort of equilibrium. The equilibrium is reached when you get to a certain time and the concentrations of the product versus the concentration of the reactants are not changing with respect to one another. That's where we get to what we call this dynamic equilibrium portion. Okay, so we're at an equilibrium, and there's a really important description down at the bottom of this, and so I'm going to pull it up and I'm going to highlight it, okay? Because it's really critical that you understand this. And that is that the rate of the forward reaction is equal to the rate of the reverse reaction. That's why we call it dynamic equilibrium, okay? Dynamic equilibrium means that these are changing. However, the rate of the forward equals the rate of the reverse, and so the concentrations of the reactants and the products don't change. Okay? So when we reach equilibrium, right, we can define that position of equilibrium as, again, it's where the rates are equivalent and therefore these concentrations aren't changing. But this is then a description of how we can plug concentrations into what we call the equilibrium constant. Okay, so this is the equilibrium constant. Here are reactants A and B. And A and B, right, are stoichiometrically linked. And the link is the stoichiometry, right, is becomes the exponent. Okay, so the molar relationship is really important. It becomes the exponent. And then if you look at the products, we've got C and D, right? And again, little c becomes an exponent and little d becomes an exponent. Okay? So this is what we call the equilibrium expression. So when we want to solve the equilibrium expression, we can use this generalized form, and this is the equilibrium constant, meaning it doesn't change. Okay, it's a constant. So the way that we evaluate equilibrium constants is by the size of that equilibrium constant, and the size of the equilibrium constant means that it goes further in this direction when it's large. Okay, when it's large, it goes in that direction. When it's small, it doesn't go very far in that direction, right? When it's small, it's a very short movement into the products. Now, that should make some sense to you because the larger K is, the bigger this number is, right? The bigger this is, and the smaller these two are, right? And so a large number means that you have a lot of product and a little reactant. A small number means you don't have very much product and you have a lot of reactant, okay? So here's the case of the small number, right? And so in this box you see there are very few of these products. And so again, this is a small number in terms of the number of products, and a large number relatively in terms of reactants. And then K becomes a small. So let's look quickly at something we would call a heterogeneous equilibrium, meaning that the the standard states of the reactants or the products are not quite the same. Um, in this case, there's not a concentration associated with the solid, therefore it's not part of the equilibrium. And if you count everything up in this, it is essentially independent of this um, solid. If there's solid present, you can't look at the concentration of it, therefore that concentration does not come into play, therefore these will be the same in terms of the concentrations of CO2 and CO. So here's one of the things that we can look at. We can look at what happens in these reactions in terms of the equilibrium concentration versus some sort of initial concentration. Okay, so you look at these equilibrium concentrations. You've got the list of the reactants and the product, and they all have to satisfy the same equilibrium constant, right? So all these are satisfying the same equilibrium constant. So when we look at something like these initial concentrations, right, we can say, okay, which direction does this have to move, right? So if I look at this and I see that there's 0 HI, I know immediately it has to move to create some HI. Now exactly how much we'll talk about in a second. On the other hand, if I have HI and I do not have any H2 or I2, I know that it's going to move in the direction of the reactants and it has to create some. But when I have this situation, I don't know, right? And I'll have to evaluate that further um, when we get towards that. Okay, and again, the same thing here. I know it has to move to the right. I know it has to move to the right. Exactly how much, again, we can evaluate in just a second here. Okay, so we're going to start by saying, look, there is something that can assist us in figuring out what these equilibrium concentrations are going to be. And that's something we're going to call the ICE table. Okay? The ICE table provides the initial concentration. You then have to evaluate and figure out what that change is going to be. And then you get to what we call the equilibrium concentration. Okay? When we get to the equilibrium concentration, we get that from the equilibrium constant. Okay, so let's look at how we might solve some of these problems where we're not at equilibrium. Okay, so think about this. There's stoichiometry involved here because you remember that we said that we had to know what these numbers were, right, for each, because we know that the K is equal to the concentration of products, CH3OH concentration, over the concentration of reactants, CO, and that one's to the first, and H2, and that one is to the second. Okay? Now, then we also know stoichiometrically what's the change going to be. Well, if I know that CO is going to react, and I say CO is going to react as X, right, I'm going to lose some X. I also know that I'm going to lose a stoichiometric amount of H2, which is 2X. But I also know on the other side stoichiometrically that I'm going to gain X. Okay? Now, if I know the starting point and I know the equilibrium point of this problem for CO, I know what X is. Right? I just set up an equation that says 0.5 minus X equals 0.15, and I solve. Then I know what 2X is, I know what X is, and I can get the equilibrium conditions. So here it is, right? Here's negative 0.35. I can then say, look, the H2 has to be 2 times that, which makes it negative 0.7, and the CH3OH is plus 0.35. You could put all those into an equation, and you could find out the actual or the actual K value, right? The equilibrium constant. Okay. So let's look at this one, right? And again, there's some missing pieces of data, if you will, and it gives you an idea of what is happening here. So first of all, I know that this is going to be plus 0.035, right? I know this is going to be 3 times plus 3 times 0.035. And I know this is going to be minus 0.035. Right? So I could figure it out times again the equilibrium. Sorry, I tried to add in that times 2 at the end there, but anyway, it is times 2, right, for the CH4 because of the 2 coefficient there. And so again, you get to these equilibrium conditions. Okay, so what else can we do with this? Well, what we can do is we can find out from given data where we are with respect to the K, as long as we know what the K is, right? If we're on the reactant side of the K over in here, right, we know that this is going to proceed in the direction of the equilibrium. So that is where we could take the data given to us, right? We could say, okay, I know that there's 0.75 of reactant A, and I know that there's 0.25 of product B. Plug it into the equation of products over reactants, 0.25 over 0.75. Compare it to the K. The K value is given here as 1.45. So if I compare that, I'm somewhere down here at maybe 0.25, right? I know that if the Q is less than the K, then it's got to go in this direction. Okay. On the other side of the coin here, what if I have 0.25 of reactant A and 0.75 of the product B? Well, I'm all the way up here, right? Meaning that I'm at 2.5. That means that this thing has to go backwards and satisfy the equilibrium condition K, right? The constant K. So I now know by using something called the Q, right? The reaction quotient, if you want to use it that way. By using Q, that I can figure out where I need to go. Which direction is this thing going to go? It's going to help us solve these problems. So here's just a generalized, right? If K is 1.45 and we calculate Q to be 0.55, it is less than K, therefore it's got to move towards products. It's got to move towards K. If it's 2.55, right, then it has to move towards reactants, reducing that ratio, and towards reactants reduces it, and you get to the 1.45K. If it's at 1.45, then you're at equilibrium. Okay, so here's an equilibrium problem. And in this equilibrium problem, we have a Kc of 0.1, right? So the K, the equilibrium constant, is 0.1 at 2,000 degrees. And it says it initially contains this 0.2 and 0.2 molar of both N2 and O2. And it says find the equilibrium concentrations of reactants and products at this temperature. All right, so we want to set up an ice table. We also want to look at the Kc, where it's equal to products over reactants. So it's the concentration of NO squared over concentration of N2 times concentration of O2. Well, I know at this point, right, that I have to create some product. So I don't really have to look for a Q at this point because I know it's going to move towards NO, right? And the way it's going to move towards NO is we're going to have a minus X, and we're going to have a minus X, and we're going to have a plus 2X, right? So at equilibrium, I'm going to have something that looks like this, 0.200 minus X, 0.200 minus X, and plus 2X. Okay, so here it is, right? Here's what they came up with. Again, I don't know why this doesn't show up right, but you guys get that when that box is there, that's the double-headed arrow. Okay, so now we got to do some math, right? So what you do with this equilibrium condition, and this would be our condition, right? Is we simply plug it into the K. And here's the K down here, and I've plugged it in and said, okay, products over reactants, 2x squared, 0.200 minus x times 0.200 minus x. That becomes 0.200 minus x squared. We could rearrange all of this, and we could get to a quadratic equation, and we'll do that when we go over this in lecture, okay? Okay, so now we're going in the opposite direction, right? We start off with no reactant, and we have product. And so again, looking at stoichiometry, if we make this plus x, right, and we make this minus 2x, right, that simplifies things a little bit for us. And so now we get 0.100 minus 2x, and we get x. And again, we're going to have to plug this into the equilibrium expression. Okay, so this one was a little easier to kind of write out, and so I've done that. And so you can see in here now that when we solved this, we got this x and 0.1 minus 2x. All right, we did that on the previous one. And then I've written out the equilibrium expression up here. And then this is that equilibrium expression with everything in it, right? And then here's the quadratic equation. So, you know, you get 0.36, you multiply the x through on both sides, you expand this. All right, I didn't do this one right? We'd have to expand this. So there's an x term in there that I didn't get. That x term would be what? 0.2x, so it becomes 0.2x or 0.4x because it's 2 times 0.2x. So 0.4x, and then I think that actually makes this 0.7x. Okay. And then again, you use the quadratic expression to go ahead and solve it. You got that on your phone. You could look it up, and we'll talk about that in lecture. Okay, so now they've kind of switched it up a little bit on us here and said you've got a reaction, the Kp now, and this isn't going to make too much of a difference, but the Kp is related to the equilibrium constant of a gaseous equation, and so these are measured in pressures, right? And so you get these partial pressures all at 0.1. And so the pressure, so now Kp is equal to the pressure of the product, right, ICL squared, right, over the pressure of I2 and the pressure of Cl2, right? And we treat those the same way we treat the concentrations, right? So now at 0.1, right, we have to figure out which direction is this thing going. And so this is where this Q comes in. So we're gonna plug in these conditions and say, okay, Q is equal to um, 0.1 squared, 0.100 squared. And it turns out if it's at 0.1 on the bottom as well, it's 0.1 times 0.1, or zero point 0.1 squared, which equals 0.1 squared over 0.1 squared, which is 1. So now this Kp is at 1, meaning that it is much less than, I'm sorry, this Q is at 1, meaning that Q is much less than, right? Q is much less than Kp, meaning that the direction that this has to go is towards products, right, to get bigger. And so we know that this becomes now plus x, I'm sorry, minus x, my bad, and then plus 2x. All right, I'm going to go back, hold on. Okay, so again, minus x plus 2x. And then we come up with 0.100 minus x, 0.100 minus x, and 0.100 plus 2x. And we could solve this thing. So again, you generate a quadratic, and we can work on these a little bit in lecture. You generate the quadratic. When you generate the quadratic, you get to a solution that is 0.0729 for x. Okay. Okay, so here we've got a case where they're kind of throwing a bunch of different things at you here, but basically they're saying if you've got 0.125 moles of H2S, the concentration is 0.025 because it's a half a liter, right? And then also it's giving you a Kc of 1.67 times 10 to the minus 7th. So in this case, you know that the direction is going to be minus 2x, right? Plus 2x and plus x, right? And so in the equilibrium condition, it's 0.0250 minus 2x and plus 2x and x. And plug all that in and set it equal to Kc, and you could solve for the x. So here it is set up. Now the next thing we're going to look at is actually plugging it in. When we end up plugging this thing in, we say, okay, look, there is a mathematical solution to this. We could take a polynomial with a power of 3. We could generate, actually, if we squared all of this, we'd get, x cubed minus x squared minus x, or plus x minus something. And in the end, what we would get is an x that's extremely small. So this number, right, 0.0250, is very big compared to what x is going to be. X, in this case, is going to be so small that it's going to have absolutely no mathematical effect on this number, 0.0250. We can go through and we can do this calculation to completion, and I can prove to you that that x is going to be very small. But the fundamental here says that if, let's convert this to 2.5 times 10 to the minus 2. If these two exponents are different by a factor greater than 3, right, and this is a factor of 5, if they're different by greater than a factor of 3, then we can drop the x. Okay, and this one has to be the larger one, right? So if it's larger than this, then the equilibrium constant by a factor of 3, then you can drop the x. It makes this simple. You simply square the 0.0250, multiply it by 1.67 times 10 to the minus 7th, and divide by 4, and then take the cube root, and boom, you got the answer. So the solution to this is actually 1.38 times 10 to the minus 5th. Okay, that's the x solution in this problem. And what they're showing here is that indeed it is so small that even after squaring 2.5 times 10 to the minus 4, right, or the 2.5 times 10 to the minus 2, even after squaring that, the difference now of this 2x squared is so small that it's not going to make any difference in the answer.